Good morning, good afternoon, or good evening, wherever you're tuning in from. We're thrilled to welcome you to Onda Corporation's recorded webinar, Unveiling the Future of Cavitation Monitoring with the CMS-0300, that occurred on May 14, 2024. Get ready for an hour packed with valuable insights and information. After watching the webinar, if you have any questions at all, please reach out to us at sales@ondacorp.com. Now, let us get started. Up first is Onda's own COO, Petrie Yam.
Okay. Good morning, everyone, or good afternoon. My name is Petrie Yam, and real pleasure to have you all here. So today's agenda will be the following. We're going to spend about 25 minutes discussing the basic principles of cavitation measurement and also review some solutions and applications data. Then we're going to switch gears. We're going to move over to the laboratory, and Nicholas Candia has prepared a live demonstration of some of our products. And then last but not least, we'd like to also open it up for any Q&A. I should also mention that to use some of the tools, there's an icon on the bottom right-hand side that there's one icon that's called Activities with three shapes, triangle, square, and a circle. If you click on that icon, one of those options is a Q&A activity. And so if you have any questions, you could ask questions at any time. We're going to answer them all at the end, do our best. We'll also maybe throw in a poll question or two, but feel free to use those tools. Okay? Okay, so let's get started. Okay, so first, today's talk is really going to be discussing how to establish a cavitation monitoring system, largely to control and monitor your ultrasonic cleaning process. And to start, let's first talk about how does cleaning actually work. It's actually quite a complex process, as you all know, but it boils down to these three steps. There's some form of mechanical agitation that's applied to the surface to disrupt the boundary layer, allowing particles to get detached from the boundary layer and get lifted into the bulk through a rinse. And with ultrasonic cleaning, of course, the mechanical agitation that's being applied is from the ultrasound. And when we think of the ultrasound, we consider three different pressure components. The first is what we call the direct field sound pressure from the fundamental sound wave. In other words, if you have, let's say, an ultrasonic cleaning tank driven at 40 kilohertz, this is the sound wave that's propagating between positive and negative pressure 40,000 times per second. And when you have that very rapid change in pressure from compressional to rarefactional pressure, you'll generate cavities or bubbles. And these bubbles exist in one of two forms. The first is what we call stable cavitation. Essentially, these are the cavities that are just oscillating in size and dimension, or above some pressure threshold, these cavities will collapse. They'll implode, what's known as transient cavitation. We believe all three pressure components contribute to cleaning, and for that reason, we need to understand it from a base level. And so with ultrasonic cleaning, though, really ultrasound is just one of several variables that contribute to cleaning. There are other variables like the electrical power delivered to the generator, the amount of gas concentration you have in your medium, the type of chemistry that's being used, the temperature, the flow rate. All this affects your cleaning performance. And for Onda, as an ultrasound metrology company, we certainly focus on the ultrasound parameters, namely, again, the direct field pressure, the stable cavitation, and the transient cavitation pressure, as well as the frequency. But the good news is a lot of these other variables affect the ultrasound cavitation. And so it's indirectly measuring these other or monitoring these other variables. And why do we do this? Of course, the interest is to be able to clean parts fully, in other words, maximize your cleaning efficiency while minimizing or preventing any damage. And so this is a process window. It's a graphic that it's actually based on real data from a Korean semiconductor company, and it shows how, as you increase the acoustic pressure in x-axis, how that affects the particle removal efficiency in the first y-axis. And so at some point, you're going to remove all the particles on the surface of your part, but at some upper threshold, when you apply excessive pressure, you're going to start to induce damage. And so that's really the trick, is to understand what those limits are and understand the relationship between how the acoustic behavior correlates with not only particle removal, but also damage. And with this, Onda provides a means to measure the x-axis, while you as a process owner, you're doing inspection and verification to understand at what point are particles fully removed and possibly damage occurs. And so how do you do this? Well, there's actually a variety of different methods that have been used with ultrasonic cleaning. And with cleaning using ultrasound, that's existed for decades, I think 70, 80 years. And there's certainly a list of methods that rely on qualitative measures, visually looking at the erosion pattern on aluminum foil strips, maybe looking at how colored vials change. But to do monitoring requires a quantitative method, and a couple different ways that have been used include a sonoluminescence method, essentially counting photons as these acoustic cavities collapse, or perhaps the more de facto standard is relying on hydrophones. And what is a hydrophone? A hydrophone essentially is a pressure sensor that is used to measure pressure or acoustic pressure in a fluid, relying on a piezo sensing element. And so that's the method we're going to be describing today. And there are no shortages of hydrophones, or some folks call them probes, but we've counted over 40 commercially available probes. More than half have been offered by tank manufacturers, and most of them provide some indication of the cavitation performance inside of an ultrasonic tank. Only two follow a standard method that was just announced 2019, called IEC 63001. And those two methods, the two solutions that support that, Onda is one of the two, and the method specifically calls out for relying on hydrophones to do spectral analysis to quantify the cavitation pressure. And Onda is one of the two. There's another outfit in Germany that also follows the standard. And so what is the standard? The standard method is based on the submersion of a hydrophone inside your fluid. Again, the piezo sensing element changes in the electrical signal as mechanical pressure is applied. And so what you're doing is you're measuring something called a raw voltage waveform, or voltage versus time, at a very highly sampled rate. But because we want to measure spectrally, we have to convert that time domain data into frequency domain by applying a Fourier transform. But voltage is still a relative measure, and to measure in absolute units of pressure, you need to correct for the hydrophone effect, so you have to apply the hydrophone calibration to arrive at a pressure spectrum, or pressure versus frequency. So if you look at, let's say, a hydrophone calibration sample, this is a calibration of one of our hydrophones called an HCT320, and this specific hydrophone is designed to measure cavitation pressures, but what you can quickly see is that the sensitivity, or the volts per megapascal value, as a function of frequency varies quite a bit. So in other words, at 40 kilohertz, you have a sensitivity of about 1 volt per megapascal, whereas roughly 95 kilohertz, the sensitivity is over an order of magnitude higher than at 40 kilohertz. And so if you simply rely on the voltage measurements, you could be misled. And so, in other words, these could have comparable pressure levels, but if you just look at voltage, your voltage signal will be a lot higher at 95. And so with that calibration, which is specific to the hydrophone, and this is true for any hydrophone, not just an Onda hydrophone, but any mechanical device that's shown here has an inherent calibration response. You need to correct for that response. And once you arrive at the pressure spectrum, then you can apply curve fitting algorithms to separate the different parts of the spectrum to say, well, here's the fundamental frequency, so this is our direct field pressure. Here's the parts that represent stable and transient cavitation. And an example of that is here's some data as an example that represent a 970 kilohertz megasonic tank. And so what you'll see typically is a fundamental peak at the drive frequency, and that is representing the direct field pressure. Again, when you have those very rapid change in the pressure, you generate the cavities. And the cavities that are just pulsing in size and dimension is called the stable harmonics, or stable cavitation, represented by the harmonics in yellow. And when those same cavities collapse, it creates a broadband signal, which is represented in red, known as transient cavitation. All three are important to cleaning. The transient cavitation in particular often correlate to damage. And so it really depends on your process, but understanding the lower level details is important. And so tying it now back to the solutions, Onda essentially offers two products. One meter is called the MCD-2000, and the other is called the MCD-1200. Both interface with the same hydrophone, the HCT320. And the MCD-2000 is the system that is often used for process development and provides you the lower level pressure components. It conforms with the standard. And it essentially combines the power of a spectrum analyzer and calculates all the parameters automatically. Now, as you develop your process, once you establish your thresholds, you evolve into process monitoring. The MCD-1200 is a good solution because it outputs two parameters, the total relative pressure as well as the frequency, but there's also a way to match with an absolute measurement from the MCD-2000. So they're very complementary, they play complementary roles. So more specifically, the MCD-2000 allows you to save 3 out of these 4 layers of data. The voltage waveform, the pressure spectrum, as well as the calculated parameters. Whereas the MCD-1200 outputs 2 parameters, the fundamental frequency as well as the relative total pressure, which is adequate for process monitoring. And so why is all this important? Well, at the end, you you're looking for an indication that correlate with other process variables, things like the drive frequency, the amount of power delivered to the transducer, maybe the gas concentration or the temperature. In all four of these charts, the red columns represent the stable cavitation, the green columns, the transient cavitation. And what you can quickly see is that, let's say for frequency, as you go higher in frequency, you're essentially suppressing the cavitation pressure. You're giving, at higher frequencies, you're giving these cavities less time to grow in size, and so they're smaller cavities. And when they collapse, the pressures are much lower. And so generally, higher frequency, lower cavitation pressure. For power, as you deliver more power, electrical power to the transducers, your cavitation pressure should certainly increase. But maybe what's more interesting here is these purple dots represent the ratio between the stable and transient cavitation. And so what you see here is at 20% power, you see that the transient cavitation dominates over the stable cavitation. But at 40%, the stable cavitation starts to dominate. So somewhere between 20 and 40% is where this cavitation threshold exists. This threshold, again, is the pressure level at which the cavities begin to collapse. And it's unique to most cleaning processes. And in this case, it's somewhere between 20 and 40%. The dissolved gases is also a very elusive variable to understand, but this is important for various reasons. Perhaps most prominently is the cushioning effect that dissolved gases may have on the cavitation. And so many tank manufacturers recommend, in fact, a degassing pre-clean step to try to remove some of the gases and limit some of this cushioning effect. But in this case, from moving from left to right, the amount of dissolved oxygen concentration is reduced moving from left to right. And as you reduce the dissolved oxygen, the cavitation pressure decreases. I would invite you to a whole paper that was written describing the physics behind this, which is available on our website. Temperature, finally, this one's also a very tricky variable because not only does the temperature change the sound velocity and change the surface conditions, the surface tension of the part, but it also essentially degasses your system. So in many ways, it's changing two variables by with the change of one variable, the temperature. In our experience, at higher temperatures, the cavitation pressures get reduced. So we've done a lot of studies, actually quite more extensive than these 4 parameters, and if you'd like to review in detail, we'd be happy to. But the idea is once you understand your system, which also includes the positional dependence within your tank, and so with a hydrophone, you have because it's a very small diameter sensing element, the HCT has a 3 millimeter OD shaft diameter. You're able to map the tank uniformity, the pressure uniformity, as a function of position. And what you'll see is that there's a number of hot spots and cold spots that are generated by the acoustic behavior. So in this case, it's a 2x3 transducer array, and this red plot is an XY plot directly above the transducers. And you actually see 5 out of the 6 transducers. In this bottom left corner, we identified essentially a dead spot from a debonded transducer. And so you certainly don't need to measure it with this much resolution, but a hydrophone is very useful to allow you to map the uniformity. Other artifacts may be standing wave effects, and in our case, we have the luxury of a scanning tank to be able to map the uniformity. So the idea is, once you establish a base understanding of your ultrasonic tank performance, now that you have a process that's established, now you want to monitor. And one of our key customers, Semiconductor Equipment Parts Cleaner, what they said is, well, now that we've done that, we want to continuously monitor by permanently mounting an HCT hydrophone inside the tank, couple it with an MCT-1200 that gets connected through Ethernet to a computer. You have multiple tanks, you're monitoring multiple cavitation signals. One of these signals is the cavitation signal, and among other parameters like resistivity and temperature. But the idea here is that you're able to identify real-time excursions so you could correct things immediately. And so this was a nice setup. It worked well, and we gained quite a bit of experience in understanding where to put the hydrophone, ensuring that if you put it in one corner, that you're sensitive to any changes across the tank. But it forced us to think, what if you're able to measure acoustically inside the tank from the outside? And so this may be a better way to do continuous monitoring, where if you mounted a sensor outside the tank that coupled inside, that would allow you to avoid any disruption to the acoustic field. It would prevent the need for cumbersome fixtures. How do you mount the hydrophone? Where do you put it? How do you hold it? And it also avoids any direct exposure to harsh chemistries or even high temperature. So mounting it on the outside has a lot of benefits, so long as you're able to correlate with the measurements inside. And so we began to develop a new sensor called the CMS-0300, and that's the emphasis for today, to be able to develop a very simple way to mount the sensor onto the outside of a tank under a dry condition. And the way you do that is you simply clean the surface. The way you mount it does not rely on any epoxies. We've identified a very high bond strength double-sided tape that is strong enough with the application of a primer. You mount the housing on, you insert the sensor, the wave washer, the wave spring, and then you lock it down with these two locking nuts. And once you have that, you can reference measurements on the inside by simply applying this expression. Because the hydrophone measurements coupled with the MCT-2000 outputs in units of absolute pressure, kilopascals, you have these three lower-level pressure parameters, the P0, PS, and PT. To translate that into a total pressure, you simply take the square root of the sum of the squares. You come up with a total pressure value, and inside the MCT-1200, there's a scale factor feature to match the measurements against this total pressure value. And that will allow you to self-calibrate the MCT-1200 with a CMS-0300 sensor with an MCT-2000 and an HCT-320 hydrophone inside the tank. And so we've done that in a 40 kilohertz tank, and we started to change different parameters like the power. So this is a plot of pressure versus time, and you can see the staircase pattern where we just changed the power level, and we saw a very good correlation. The red represents the measurements on the outside, called the CMS, and the blue is the HCT on the inside, and we saw a very strong correlation, an R-square of over 0.99. So we were quite excited about that. And then similarly, if you look at the pressure as a function of time, reducing the power, you can see that when you change the power, your pressure values will change from the CMS-0300, as well as, when you reduce it, you'll also see the changes. And so this method allows you to make these real-time measurements and continuously monitor. We've partnered with one of our key customers at GE Aviation. It's an aerospace company based in Canada. This site was, and they were setting up the CMS sensor on a side-firing system. And they had 3 or 4 transducers that were opposing each other in a 25 kilohertz tank. But they saw good correlation. And so that was the key. And with that type of information, once you establish that monitoring method, you could proliferate this across multiple tanks. So if you have a wet bench with multiple tanks, now you could dedicate CMS sensors to each tank, interface it to an MCD-1200 through Ethernet, go to a network switch, and then from a computer, now you can do SPC tracking for all your different tanks. All with the ability to reference measurements to an absolute pressure measurement tool, the MCD-2000. And so with that, that's kind of a short overview of some of our solutions, and that concludes kind of the quick overview.
Okay, so next I'm excited to introduce Nicholas Kandia, our lead scientist who sees over all Onda's cavitation measurement products, who will be our official demonstrator today with some narrative assistance from Petrie Yam.
What Nicholas is showing here is first our hydrophone. So the hydrophone itself is, the construction of it has the piezo sensing element at the distal end, at the working end. You'll see that there's kind of an orange portion that by design is developed to pot the sensing element, but also to mechanically decouple it from the rigid shaft that you see in silver. So that's important because you have to localize the measurement to a point. And a lot of these hydrophones, maybe the sensing element is rigidly mounted to the shaft, which makes the entire length sensitive to the acoustics. But really, you want a point sensing measurement. That entire construction is embedded inside a Teflon tube. It's a fluoropolymer called FEP, and that allows you to measure within chemistry. The handle itself in blue is a plastic. It's a Delrin plastic, and that is waterproof, but it shouldn't be submerged. If you want to measure in chemistry, really you should just expose the shaft portion. So from there, a cable comes out, and the cable then gets connected to a multi-pin connector. The connector is it's a special connector with memory embedded inside, which stores the acoustic calibration for that specific hydrophone. So when you connect that hydrophone to one of the meters, it'll automatically read that calibration table and apply it. So in this case, Nicholas right now has it connected to the MCD-2000. You'll see that the serial number is being read, which means it's applying the calibration table properly. And right now he's got the hydrophone submerged in a 40 kilohertz tank. And so if we, I should mention the hydrophone is also held by one of our accessories called the Hyde slide assembly that allows you to manipulate the hydrophone in X, Y, and Z. It also helps you kind of track the rotational orientation of the hydrophone. This is all in an interest to make repeatable measurements. Going to the same location, holding it in a very consistent way will affect the measurement repeatability. And ideally, the sensitivity of the hydrophone is the sensitivity has the maximum sensitivity is when the firing angle is normal to the tip of the hydrophone. And so, okay, so if you turn on the tank, maybe we could just first show a very simple static repeatability test. And I could show you the software quickly. So there's several different tabs to the software. It's very simple to connect with the MCD2000 through Ethernet. On the back of the meter, you just simply connect to a LAN port or directly to a computer, and you type in the IP address that is displayed on the MCD2000, in this case 192.168.10.175, and you'll be able to connect directly to the meter. Once you connect, to set up your measurements, you can look at the settings, where the main settings like the averaging time, 1 second, you want to log it over, let's say 10 minutes or 10 seconds, a log rate of 1 data point per second. There's other features where you can do auto zeroing, apply the something called the gain matching correction to match data. And then because the files are quite large, even though the system allows you to save many layers of data, you may not want to always save those layers of data just because they take quite a bit of space. But you have the option to save the spectrum or the raw voltage waveform in either ASCII or binary format. And then there's a feature around forcing the system to detect a certain frequency. So there's a number of features that are allowed. To look at data, you could go through the file manager. We'll be going through all these other steps after we collect some data. So I think right now Nicholas has the tank set up for this 40 kilohertz system. Now Nicholas, if you could hit record and log data over, say, 10 seconds or so. Okay. And so Nicholas just captured some data. And the data that we're looking at now is this data that we just collected. Again, it's a 40 kilohertz tank showing these pressure parameters of P0, PS, and PT. And for each one of these data points, we also save the spectrum files, so that's what the ASPEC files are. Now, if you want to, there's two ways to analyze the data. One, you could simply export the data. In ASCII, you could use programs like Microsoft Excel to take a quick look. We also have a nice analysis tool built into the software where you can simply select the folder that you want, that you just collected, that you want to analyze, and look at not just the trend plot, but also the spectrum. And so you can look at multiple data points. Now the data here is quite repeatable, so you don't see much difference from point to point. But if you, let's say, remove the green, you can see the other red point, the data point 6, right underneath it, data point 5. So it's a nice way to just quickly be able to look at and compare the performance or the acoustic behavior at different points. So there's a couple different modes. This was the log mode, and let's say if you wanted to map the uniformity, you could use a tap mode and then compare spectrum files. Okay, so that's generally how the MCD-2000 works. You get an output, a statistical summary. You can look at the raw data, and this is our reference measurement. And so now what Nicholas is going to do is show you. We're going to demonstrate the CMS-0300. Okay, so the CMS-0300, as we discussed, the first step is to really clean the surface. Actually, the first step is to identify a location on your tank. And so in this case, Nicholas found a spot. He cleaned it with some IPA. He's not going to do it here, but then you apply a primer onto the surface. Let the primer dry for maybe a minute or two. It'll start to haze. You're activating the surface, and then the CMS housing, you simply remove the double-sided tape, and you put it on. And once you do that, essentially you have immediately, I think 30 or 40% adhesion strength, which is sufficient to complete the installation. But if you let it cure overnight, I think it reaches 100%. But once you make contact to it, it's immediately strong enough. So the housing gets mounted onto the surface, and then you connect the cable onto the CMS sensor, and then you insert the sensor, apply the wave spring, which allows you to apply a constant force onto the CMS sensor, and then you apply both locking pieces to lock the sensor in place. Now, that's it. That's essentially how you mount the sensor on. I will say one thing that, okay, so one detail is that the CMS sensor on the side that's connected to the wall, there's a rubber coupling. So again, you have to make sure it's clean. What Nicholas just showed is he showed that how an example of mounting that CMS sensor inside a tank. So sorry, if you could show that again. And again, the reality is a lot of these tanks have quite a bit of other components that are mounted, maybe electronics, a heater, maybe insulation. So you do have to find a good spot to directly couple to the acoustics. And so once you find that spot, the cable gets routed out and connected with an MCD-1200. And this MCD-1200 then it's ready to measure. So now when you connect the CMS-0300, after doing that, now let's demonstrate how to match the CMS with the HCT. Right, and so right now he's got a hydrophone inserted inside the tank, and the measurements from the MCD-2000. If you could show the measurements on the MCD-2000. So that's the absolute reference measurement that's going to be applied, and on the MCD-1200, we're going to enter those reference values under the scale factor feature. And so he's simply applying those parameters inside the 1200. And once you have that, you hit the record button. You start the matching routine by hitting record again. To match the CMS-0300 that's interfacing with the MCD-1200 with the HCD320 that's connected to the MCD2000. Now, if you do this for, let's say, within a high volume production line, oftentimes a lot of these wet benches are have a lot of controls in place, and different components that are available within the configuration includes a PLC. So the PLC on the bottom right, that is connected with a network switch. The network switch can interface to all the different MCD1200s. Then you have an interface, which is the item on the top, showing the display. And if you want, you could even interface this entire setup with your own automation software. And so that's quite common, and that's something that we have prepared here. Okay, and so right now, for this system, this is the 40 kilohertz system, and we've developed a software to just connect through IP. And so this is real-time data that we're displaying on the left-hand side. 40.3 is the frequency, 49.7 is the pressure. Oh, it looks like Nicholas just changed the power to the generator, and so he's increased it from 40 plus to 70 kilopascals or so. And so now if you want to reduce it back, and so let's say your limit was 50, and you could see the green turn to red, right? And so there's different ways to sound alarms. And in this case, Nicholas has just changed the power from, I think, a low power of maybe 50% up to 100%, back to 50%. Other things that can change the behavior of the tank, of course, it could include things like loading your parts. Let's say if you wanted to put some parts into the tank, if you could just monitor the pressure. In this case, because you're adding a part, you're changing the reflections, it actually reduces the total pressure inside the tank. And so you can see it's quite consistent, but you notice that there is some sort of change to your system. If you take the part out, oops, and so the waves are bouncing a little bit right now, but when it stabilizes, the pressure should come back up. So that's just kind of a quick demonstration of things that variables that will affect the acoustic behavior. In another tank that we have this system, which is a very nice system as well, that allows you to switch the frequency. It's a 7-frequency system. And in this case, you can see the first frequency that's set is at 80 kilohertz, measuring at about 300 kilopascal. Looks like Nicholas just changed the frequency to about 120 kilohertz, which also affected the pressure. Just went up to 160 kilohertz, again changing the pressure. And then ultimately the 260 kilohertz, which reduces the pressure further. And again, in this case, as you go higher in frequency, the pressure levels do reduce. Once you understand that, you evolve into process monitoring, and with that you can rely on the CMS sensors that are mounted on the outside. They're a little more production worthy, and so long as you could reference back to the HCT measurements on the inside, which you can do, let's say, during your quarterly PM cycles, check your system. But on a daily basis, you can rely on your CMS sensor to just continuously monitor.
Thank you for viewing our webinar, Unveiling the Future of Cavitation Monitoring with the CMS-0300. Your time and interest are greatly valued, and we look forward to the possibility of collaborating with you soon. If you have any questions or require additional information, please feel free to reach out to us at sales@ondacorp.com. Once again, thank you.